Energy cannot be created nor destroyed. It can only be changed from one form to another. This is the law of conservation of energy. In other words, the entire energy of the universe is conserved. When physical or chemical changes occur, they are generally accompanied by transfer of energy. In order to understand better the energy changes taking place during a reaction, we need to define two parts of the universe: the system and the surroundings. The system is the specific portion of matter in a given space that is being studied during an experiment or an observation. The surroundings is everything else in the universe that is not part of the system. Let us consider this illustration where the universe is represented as the system and the surroundings. The system is this specific part of the universe that is of interest to us. In this case, the system is the block of ice. The rest of the universe outside the ice block is the surroundings. We can go further and have a microscopic view of the system, which is basically water molecules strongly held together by attraction forces. During most processes, energy is exchanged between the system and the surroundings. When we talk about energy changes, we talk about the energy change of the system and not the surroundings. It is very important to get that. Unfortunately, we cannot be able to measure the energy change of the system directly. So we measure the energy change of the surroundings. And because energy is neither created nor destroyed, then the energy change of the surroundings is equal to the energy change of the system. In other words, if the system loses a certain amount of energy, that same amount of energy is gained by the surroundings. And if the surroundings lose a certain amount of energy, then that same amount of energy is gained by the system. So an energy gained by the surroundings means an energy loss by the system. A chemical or physical change is endothermic if heat is absorbed by the system from the surroundings. In the course of an endothermic process, the system gains heat from the surroundings. Therefore, the energy of the surroundings decreases while that of the system increases. And so the temperature of the surroundings decreases. Let us consider our illustration. Heat comes from the surroundings into the system. This heat energy is applied to the water molecules, which vibrate more vigorously and overcome the forces of attraction, and the ice melts. So water molecules in liquid water contains more energy than the same molecules in ice. And so in an endothermic process, the final enthalpy of the system is larger than the initial enthalpy. Enthalpy change is equal to final enthalpy minus the initial enthalpy, and therefore the enthalpy change is a positive. On the other hand, a chemical or physical process is exothermic if heat is released by the system into the surroundings. In the course of an exothermic process, the surroundings gain heat from the system. Therefore, the energy of the surroundings increases while that of the system decreases, and so the temperature of the surroundings increases. Let us again consider our illustration, this time the reverse process, that is freezing. During freezing, the water molecules lose their kinetic energy and move less vigorously. This energy is lost into the surroundings in the form of heat. As more and more energy is lost from the system, the water molecules slow down so that stronger attraction forces build and the water freezes. So in an exothermic process, the final enthalpy is less than the initial enthalpy. So enthalpy change is equal to final enthalpy minus the initial enthalpy. So the enthalpy change is a negative. We can represent these processes using energy level diagrams. On the x-axis, we have the reaction progress, and on the y-axis, we have the energy in kilojoules.